Hello, my name's Chelsea and this video is part of a series of A-level content that is all about learning differentiation. The image of the worksheet in this video, as well as other maths related content, is over on my Instagram page because I love me some numbers. Okay, you all know the YouTube drill now. This content is free from me to you. Therefore, it'd mean a lot to me if you hit that like button, press subscribe and wait for it, go follow me on Instagram, just so I know that maybe this is quite useful and I should continue doing it. Thanks for watching.
Okay, worksheet 1, Differentiation Introduction. At GCSE, you were taught the general equation of a straight line, and that is y is equal to mx plus c. And you were also taught that if this equation were plotted on a graph, then this number here, the c, would be the y-intercept of its graph, and the number in front of the x, this m here, would be its gradient. Now remember, you were also taught what the gradient is. The gradient is the slope of the line. I always like to think of roller coasters when I think of gradients. Imagine sitting on a roller coaster and just going along, and all of a sudden you start going up. That's the gradient increasing, and you're going up and it's getting steeper and steeper. That's the gradient increasing. So that's what you learn at GCSE. You could be given an equation of a straight line and you could just pick out the gradient straight away. Now, what happens when you don't have an equation of a straight line? What happens, say, if you have a quadratic, something like this? Really simple, y equals x squared. How do you find the gradient of this? There's nothing you've learned that says, oh, you just pick out a certain number from the equation. That doesn't happen with these. And the reason why that doesn't happen is because the gradient of this graph, when plotted, isn't constant. Like, its gradient keeps changing all the time. From this point here, there will be a different gradient to this point here, to this point here, to this point here. The gradient is continuously changing. So we don't have this one value for the gradient that we can pluck out of the equation. And we don't have this one value, like a certain number for the gradient, because the gradient is actually a variable. It's a function as well. So the way we actually find a gradient of any equation is to use differentiation. To differentiate a function is to find its derivative. The derivative is what just tells you what the gradient is, but it tells you what the gradient is at multiple values of x. Like I just said down here, the gradient of this graph is different all along its curve. It's different for different values of x. The derivative tells you what the gradient is of a curve, but for all values of x. If you want to know the gradient at a certain point, you plug in a certain value of x. So the way you differentiate a function depends on what the function looks like. As you know, functions can look very different. We're just going to start with the first and probably most simple method of differentiation based on a function that looks like this. So if y is equal to x to the n, then its derivative is given by f dash of x, which is equal to n times by x to the n minus 1. This f dash of x is the notation we use to show, we're talking about the derivative of the function f of x. Now, you can see lots of different notations for derivatives. This is because so many mathematicians have come and gone and invented their own. We've got Leibniz, I don't know how to say it. We've got Newton. They all came up with their own notation. So these are the different notations, but they just mean the derivative of a function y equals x or y equals f of x. So let's just look at some quick examples now. Let's see how this method can be used. We want to differentiate y is equal to x squared. So in the method above, this n here is actually equal to 2. Therefore, if we differentiate y equals x squared, this 2 falls down. This is how I remember it. This 2 falls down, and then this 2 has a 1 taken away from it. So we get 2x, 2 minus 1 is equal to 2x. And here I've used the notation dy by dx. Next, to differentiate y is equal to the square root of x, it's always easier to rewrite your equations in power or indices form. So for this, if I want to differentiate it, it is so much easier to write it as y equals x to the half. If we want to differentiate y equals x to the half, remember this half floats down and a 1 is taken away from it. So we get the half here times by x to the half minus 1. So we get a half times by x, so minus a half. So we get a half
and I've just
times
seen
by
I've got a
x,
double
so
equal
minus
sign
a half.
there.
And
Let's
then,
change
like
that.
I said, I've used indices. The minus sign brings the x down into the denominator, and then the half changes it to square root. So this is the derivative. And like I said, the derivative gives the gradient of that function at any point. So if we have the function or equation y is equal to x squared, its derivative is 2x. This means that this is the gradient of this curve for any value of x. But if, say, you wanted to find its gradient at x is equal to 2, you would substitute x is equal to 2 in here. So we get the gradient as 4. And the final section, just a quick extension on the rule that we've gone over above. The rule doesn't just hold for if you have a function with one term in it, like just x squared. It could have x squared plus x. It could have x cubed plus x squared plus x. You could still differentiate it using this method above. And this is what I've written here. So if y is equal to x to the m plus x to the m, then use the same method to differentiate that. You do each term using that method above. In addition, if you differentiate a function that has a number in it, say you have like x squared plus 2, that plus 2 part is what we call a constant, and those always differentiate to 0. They just disappear, basically. When you're doing the workings, you can literally just remove it, but here I've included why it actually differentiates to 0, like why does it happen. So if you just had the general equation y is equal to 2, then again, as you should always think, let's rewrite this with powers. You could actually rewrite it as y is equal to 2x to 0, because remember, x to 0 is 1. Anything to the power of 0 is 1. If we want to differentiate that, we use the same rule that we've just learned. This 0 floats down, and then 1 is taken away from the 0. Well, anything times by 0 is 0. So we can see the derivative or the gradient is 0. So this proves that numbers or constants differentiate to 0. And you can see it also makes sense. The graph of y equals 2 is just a horizontal line, which, doesn't have a gradient. And that's what we've just shown here. Coming back to our equation of a straight line, let's just marry those things up. So we had the equation of a straight line, y equals mx plus c. And you know from GCSE that m is the gradient. Suppose you didn't know that. Suppose we didn't know that method. We just wanted to use the differentiation method. Okay, so differentiate y is equal to mx plus c. Again, I haven't done it here, but you can write the indices notation. So we've got a little 1 above this x. Therefore, when we differentiate this, the 1 floats down, so we get 1 times by m x to the 1 minus 1, and then the constant c, it will be some number, so we know this differentiates to 0, as we've just seen here. Therefore, the derivative reduces to m. Oh, well, we do actually know that, because we know from GCSE that m is the gradient, so the derivative should be equal to m. Perfect. And one final example, I've just put a quick one in here where we find the gradient and then we find the gradient at a certain point. So find the gradient of y equals x squared at x is equal to minus 2. So the gradient at any point we found above we know is 2x. But the gradient at x is equal to minus 2 is found when we substitute a minus 2 in here, i.e. we replace this x with minus 2. And so we get the gradient at that point as minus 4. So we know that y equals x squared looks something like this. And therefore, we've just found that the gradient at minus 2, which might be about here, is minus 4. And as always, there are some questions to test your knowledge on this worksheet. Thanks for listening.